Welcome. In this lecture, let's see how to code the sum of subsets problem based on the explanation what I have given in the previous video. As usual, we will make use of online GDB programming environment. We choose C programming language to implement the solution of sum of subsets problem. I'm not focusing much on reading the data from the keyboard and all. I'll use initializations as much as possible because my emphasis would be more on coding the backtracking algorithm rather than other auxiliary functions of reading the input and then printing the output in a formatted way. I'm leaving all those things for you as an extension of exercise. So let's take the problem what we have seen in the exercise itself. The problem consists of 5 weights. So let me define n as 5. And then in this problem, we need to have a weight array to store the weights. And we also need to have a solution array to store the solution as usual with the principle of backtracking. So I declare a weight array. And as I said, I'm initializing it. I'm going to take 5 weights. So I'll put -1 in the location 0 because we will be working with indices from 1 to 5. So the weights as given in the exercise problem in my previous lecture are 2, 4, 6, 8, and 10. And let me declare the solution array as well, which would be a global array. We'll initialize location 0 with -1 and all other locations as 0. I hope we have 5 zeros here corresponding to x1, x2, x3, x4 and x5. Yes. And then let's choose the value of m as 12. So you find that because the value of m equal to 2 is one solution, 2 plus 4 plus 6. That's one solution. 8 plus 4 is another solution. And 10 plus 2 is another solution. We have a total of 3 solutions. So seems to be a good problem to explore. So because at the end you have to print the solution and you already have some experience with n-queens problem, I'm directly coding the print function. So the print function will have a local variable I which will run through the locations of x to find out the n tuple. So I plus plus, it will print the n tuple in one line, and at the end of the solution we'll add a new line so that you can see the solutions one per line. So let me close this window so that you can have a better view of the solution. Now let's code sum of subsets. Let me name it as SOS. And as we have seen in the previous video, we take a 3 tuple S, K and R. So int S S stands for the sum of the weights included so far at level k. So the second parameter is the level k, and the sum of the remaining weights at level k. So there are only two possible values for xk equal to 1 and xk equal to 0. So I can as well write a for loop for these two values, but because there are only two values, and there is also one more criticality, the bounding function is different for the case of xk equal to 1 and for the case of xk equal to 0. So what I do is I obviate the for loop and I unfold the for loop and write both the cases one after another. So that's equivalent to the for loop rather than writing a for loop for two values, and in the for loop once again identifying the case of xk equal to 1 and xk equal to 0 unnecessarily complicates the code. So we say x of k equal to 1, we choose x of k equal to 1 to start with, and then if the previous sum yes plus w of k, the kth weight is considered, is less than or equal to m, then we know that it satisfies the bounding function. And if it satisfies the bounding function, there is a possibility of sum being equal to m as well. If the sum is equal to m, then we print the solution. Otherwise, we recurse and then make the newly created node as the new node. So we call SOS with sum being incremented by adding the weight wk. The level becomes the next level k plus 1, and the remaining weight is decreased by w of k. So that completes the branch corresponding to x of k equal to 1, or the child corresponding to x of k equal to 1. So after this recursive call returns, we know that we have to explore the other possible solution with x of k equal to 0. So we store x of k equal to 0 and we check. Now we need not check the condition that s plus w of k less than or equal to m for the node corresponding to xk equal to 0. We have seen that in the previous lecture. We only have to check whether s plus r is greater than or equal to m. Then we call sum of subsets with the same value of s, of course for the next level k plus 1, and r is decremented by w of k. So that's pretty simple. That should complete the coding in accordance with the explanation what we have seen in the previous lecture. I hope there are no mistakes. Anyhow, if there are any mistakes, let's see. We'll find out while the program is being compiled and executed. And now you have to make a call, SYS, with S as 0, K as 1, and R as the sum of all the weights. Let's see what is sum of all the weights. 4 plus 2, 6, 6 plus 6, 12, plus 8, 20, plus 10, 30. So I'm not looking at reading the inputs and then calculating the value of R and then invoking the function. I'm just trying to focus on this, how to code the backtracking solution for sum of subsets problem. Other things I have taken as initializations. So I hope this completes the coding. Let's try to run this. Yes, there are errors in function main. We need a semicolon. I think I forgot the semicolon. Yes, I forgot the semicolon here. So there is a segmentation fault, which means that there is some kind of runtime logic. So let's see. Yes, we did not check for the terminal condition. We know that if k is greater than n, then you have to return. We forgot the most important condition. As I said in the previous lecture, once you reach the value of the level n plus 1, you no more expand the nodes. You stop there. So the same thing is converted here as if k greater than n, return. So let's see. Yes, that gives us all possible solutions. The first solution is 2 plus 4 plus 6, 12. Then this is 2 plus 10 is 12. Then 4 plus 8 is 12. Three possible solutions are there, and it has given all the three possible solutions. I hope you can improvise the program by adding all the auxiliary functions of reading the input and then giving a very pleasant output. We'll stop here and thank you.